that you can merge them. But these are kind of little hacks you have to do to get this to work sometimes. Okay, so will it converge? The answer is yes. To a global optimum, no. We've seen many cases where it would get stuck in something that's not the best scoring clustering. So will it always find the true patterns in the data? Well, not clear. It's not even clear what the true patterns are. You haven't defined that, right? There are variants of clustering where you might define what is the right clustering and then might try to learn to cluster, but as defined here, there's no right clustering, so there's no way for it to be guaranteed to find the right clustering, right? The patterns are very, very clear. The data is nicely segregated with enough initializations. Probably you'll find what you're looking for. Will it find something interesting? Again, it depends. It also depends a lot on your feature space, right? Because measuring these Euclidean distances, if those are not meaningful, you're going to find non-meaningful clusters. Okay? So something to think about there, sure, it's a past exam question at some point. You can find in one of the old exams is, well, can you run something like k-means where you use a similarity measure, essentially a kernelized version of k-means, where you use any kind of similarity measure rather than just distance-based clustering, right? People use it? Yeah, people definitely use it. I mean, it's one of the standard ways to analyze your data and try to discover patterns. How many clusters to pick? You try many things, and you see what seems to work out best. The natural thing to do is something like what you do in supervised training. Let's say you had some on the horizontal axis, number of clusters. And then you'd have 1 cluster, 2, 3, 4, 5, 6, and so forth. You then, 1 is maybe not that meaningful, so let's start at 2. You run your k-means from some initialization. Maybe you have a score. This is the score. That's over here. Another initialization, maybe you land here, another one here. You run a bunch of initializations. This is your best one. Then with 3, let's assume your best score is here. With 4, maybe it's here. Then maybe with 5, it's here. 6, it's here. What you see is some kind of pattern where there's a knee in the curve here, and typically you'd pick your number of clusters corresponding to that knee point. You say, well, I know that more clusters will always allow me to get a better score because I'm minimizing sum of distances, and the more centers I have, the more flexibility, so the better I can do. But at some point, it starts not helping much to have more clusters, and so it might not be meaningful to keep adding those clusters, and you want to be right here, right before you kind of get this diminishing return. Or maybe you try a few numbers for k right here in that area. Look at your data that way, see what you can find. So this is one way to cluster. That's k-means. It's a very global way of measuring distances. You're always looking at a cluster in its entirety and looking at the mean for that entire cluster, and everything needs to be close to the mean. Okay? Now, agglomerative clustering works very differently. It starts bottom up. It merges very similar instances and it incrementally builds larger and larger clusters out of the small clusters. So you could start with every data point being its own cluster, and if you have a close neighbor, merge them together in a slightly bigger cluster and keep going, right? So at all times, you have a set of clusters. Initially, each data point is its own cluster. Repeat, pick the 2 closest clusters. Haven't defined close, but let's assume we have a measure of close. Pick the 2 that are closest together, merge them into a new cluster, and keep going until only 1 cluster is left. You might say, well, only 1 cluster left. We already know everything's going to be in that cluster. But the idea here is that you have different resolutions of clustering that come out. You can browse your data at different levels of resolution this way. Whereas when you have only 1 cluster left, of course, there's not much you can do, but you can see when there's 2 clusters left, 3, and so forth. It will be some kind of tree structure in which way you can browse your data. Okay? So you'll merge 2 points, another 2 points, and you'll get this kind of tree structure being built up that at the top of the tree structure, you'll have all your data clustered together, but then you can go down and see at different granularities where things are. We need to measure distance. You can measure distance in many ways. Measure distance between clusters. One way to measure distance between clusters is the closest pair. What that means is for 2 clusters, you look at all their points, and you see which 2 points, one from each, where you have to take 1 from each cluster, gives you the smallest distance, and that's the distance between the 2 clusters. You can look at the furthest pair. That's complete link clustering. There you want all points in your cluster to be very similar rather than just having some kind of connection between points. You can look at the average, which is something in between. You can look at something that relates to variance, which is a lot like k-means. Depending on what you use, you'll get a different hierarchical clustering out here. Here's an example of clustering in action. So a lot of you might have used this. Google News. What's happening? A lot of news articles come out. They're not labeled. Nobody's telling Google this is label 1, this is label 2, and so forth. What's happening is that all these different outlets have articles, and it turns out that there's a lot of articles in this snapshot about heavy fighting continues as Pakistan army battles Taliban. It's from a few years ago. See that there's, in this case, 3,824 news articles that ended up in this one cluster. Now, this is text. So the way this cluster is represented here is that there's some kind of scoring metric in terms of which of the actual articles is the most representative. That's shown. If you had something more numeric, you could actually show the mean that represents that cluster, but for text, it's not that clear what that would be if you did that. And so articles are clustered. Here is another cluster. This one has 2,492 articles. Here is yet another cluster. You can see that there's a little bit of supervision they did here. So they cluster news articles, but they also had some supervised data somehow to decide that these first two clusters fall under world, the next two clusters fall under business, these two fall under US, and so forth. There's a combination of some supervised learning and clustering to give you the results here. Right, any questions about clustering? Okay, let's stop here for today, and next time we will look at some decision trees and neural nets.